Log on, tune in, find out. Another good idea from Cambridge.
Of this afternoon is Daniel Persson from Chalmers Institute, and he will talk about, as you can see, wall crossing and related issues.
Thank you, and thank you very much for the invitation. It's great to be here. It's a fantastic place. So my talk will be about some recent developments in the wall crossing story, maybe the never-ending wall crossing story, which makes some key use of a certain duality between quaternion-Kähler geometry, which appears as moduli spaces in string compactifications, and hyper-Kähler geometry, which appears in supersymmetric field theories. So this is some joint work with Sergei Alexandrov and Boris Piolin, which appeared recently. So first, some motivation. So the main motivation is perhaps that we want to understand completely the hypermultiplet sector of a compact Calabi-Yau compactification of string theory. So this is some n equal 2 supergravity theory in 4 dimensions. And we know, since a very long time, the work of these people, 2/3 of which are here, or maybe not here, that 1/3 of which is here, that this moduli space, or this effective action, will be corrected by instanton effects coming from D branes and NS5 branes. So in this talk, we will simply suppress these effects. They are exponentially suppressed in the weak coupling limit. I will focus on the D instanton effects, and there a key problem is to understand wall crossing. So in order to get you into the right mindset, let me review the 2 main players of this talk. So the first one is perhaps familiar. So this is the Coulomb branch of n equal 2 Seiberg-Witten theory if you compactify it on a circle. So this is a hyper-Kähler manifold called M prime. So it's hyper-Kähler, and it's known that this receives instanton corrections from Euclidean BPS states that can wrap the circle. On the other side, we have the hypermultiplet moduli space for a type 2 Calabi-Yau compactification. This I call M. This manifold is equipped with a quaternion-Kähler metric, which is a bit more complicated. And as I just said, this will receive instanton corrections from D branes, which are really Euclidean D branes which wrap some cycles in the Calabi-Yau. So we know, following a lot of work the last few years, that wall crossing in this picture is encoded in holomorphic symplectic geometry. And it's very natural then to expect that the wall crossing on this side, as I will explain, should be contained in holomorphic contact geometry. And the main question then, as is basically the motivation for this talk, is how to lift the wall crossing formula that was provided for us by Consiverts and Soibermann to contact geometry from symplectic geometry. And in fact, the answer to this is one should use the so-called QK-HK correspondence. It's a duality that takes you from this stringy moduli space to a hyper-Kähler modular space of the same type that appears in Seiberg-Witten theory on the Coulomb branch, but equipped with a certain line bundle over it. And the task is that, in fact, you can describe wall crossing in string vacua in terms of this line bundle. So you can use a lot of the techniques that were developed in field theory and, in fact, use them in the string context. So the outline of my talk is as follows. I will exactly, yeah, definitely. The CMAP is part of it. Yeah, so in fact, one example of this correspondence is in fact the rigid CMAP versus the local CMAP. So that's an example of a pair of manifolds which are related in this way. So I will come back to that. So I will start by giving a brief review of some aspect of this hypermultiplet moduli space. Then I will give you an idea of what this QK-HK correspondence is about. I will then review the story of wall crossing in Cyber-Witten theories, and I will apply this correspondence to describe wall crossing in n equal 2 string vacua. And I will end with some summary and some future prospects. So we take type 2 string theory and we take some compact Calabi-Yau threefold, and we know that the associated moduli space must split into two factors because of supersymmetry, one of which is a special Kähler manifold. This is the vector multiplet sector of the theory, and the other one, which we are interested in here, is a quaternion Kähler manifold that encodes the hypermultiplet vacua. And the key thing here is that this is quaternionic, so its holonomy is contained in SU2 cross SPn. So there is always this SU2 factor in contrast to hyperkähler geometry, which just have this SPn factor. Now, it's very useful to take a sort of look at this from a T-duality perspective, which is precisely the C-map. So as an example, let's take type 2A on X and type 2B on the same manifold X. So if you start in 4 dimensions, you have the vector multiplet moduli space here, which is a special Kähler manifold that encodes the complex structure of this Calabi-Yau. If you compactify it on a circle to 3 dimensions, it will get enlarged to some bigger space, which turns out to be quaternion Kähler. On the other side, we look at the hypermultiplet moduli space on this side, which if you compactify that, it just goes along for the ride. So now T-duality will exchange these two manifolds. So this is sort of the stringy version of the C-map. And what it does, it maps from special Kähler to quaternion Kähler, and it maps black holes to instantons. So in this particular example, for instance, we would have some black hole states here, which correspond to D3 branes wrapping 3 cycles, and these will then be mapped to D2 brane instantons on the other side. Now there is a similar story if you would start, say, the vector multiplet sector in type 2A, and if you combine this with mirror symmetry, in fact, there is a unification of moduli. So in 3 dimensions, you basically have just one moduli space, and it encodes all instanton effects in string theory. Now there is a kind of a baby version of this, which if you go to n equal to field theories. So you start in 4 dimensions on the Coulomb branch of Cyber-Witten theory, where you have some modular space of vacua. And if you compactify that to 3 dimensions, that will also get enlarged to some manifold M prime, which is then hyperkähler. So this is called the rigid C-map. And this maps in the same way Euclidean BPS states that become instantons in 3 dimensions. And as we have learned in recent years, starting with the work of Gayotto, Moore, and Neitzke, that in fact this procedure encodes the wall crossing behavior of the BPS spectrum in 4 dimensions via the metric on this moduli space. So this is the story we would like to use. But first I must explain how you convert from this quaternion Kähler geometry to hyperkähler geometry. So the QK-HK correspondence tells you that if you take some 4n dimensional quaternion Kähler manifold equipped with a certain U1 isometry, you can associate to this a dual manifold which has the same real dimension and is equipped with a hyperkähler metric and has a rotational isometry as well. But this manifold is equipped with a certain line bundle with a hyperholomorphic connection. So I will explain what that means in a second. Now, this is based on work of many peoples. The original idea from our point of view was discovered by some unpublished work of Andy Neitzke and Boris Piolin. And recently we found out that this was discovered independently in the mathematics literature in 2007. And in fact, some example of this is contained implicitly in work by Stefan and Martin Rocek in Kurman Wafa in 2006. And recently we also found out that it's being investigated by Hitchin and by Andrew Swan and others, as was announced in fact in this very room about half a year ago. And also Stefan has found some clarification on this and new examples recently.
Is it related to the Swan bundle?
Yes, it's related to the, well, it is not, it goes via the Swan bundle. I will explain in a moment how it's related to the Swan bundle. So what it really means is that you have some line bundle over M prime, and hyperholomorphic means that it is in fact holomorphic with respect to a whole CP1 of complex structures, similarly to hyperkähler, which is scalar with respect to a whole CP1 of complex structures. So this means that its curvature is in particular type 1,1 in all complex structures. So this is like a generalization of a notion of Young-Mills instanton to hyperkähler spaces. So to sketch the construction, I will sketch it from one point of view. The idea is you start from some quaternion Kähler manifold M, which has a rotational isometry which lifts to some U1 action. This Killing vector lifts to some U1 action. And you lift that to the Swan bundle, or the hyperkähler cone. So you go from M up to hyperkähler cone, which is a certain R4 bundle over M. And this isometry actually becomes triholomorphic on this Swan bundle. So it's holomorphic with respect to all complex structures. And then you can perform a hyperkähler quotient with respect to this isometry. And what you end up with is a hyperkähler manifold, M prime, with the same dimension as this M you started with, but with this additional structure of a hyperholomorphic connection. So pictorially it goes like this. Start here with M, uplift to this bigger space, this hyperkähler cone, and then you quotient down and you end up with this manifold M prime. Now the simplest setting to actually understand this correspondence is in terms of twistor geometry, and that's also the framework in which you describe wall crossing. So let me review how that goes. Well, okay, first let me give you an example. So the simplest example perhaps, or one of the simplest that's relevant for us, is if you just take M prime to be flat R4, the dual space will be the so-called universal hypermultiplet moduli space, which is this four-dimensional coset space. Another more general class of examples are these CMAP spaces. So this is really if you take the local CMAP relevant for supergravity, then via this correspondence you construct the hyperkähler manifold coming from the rigid CMAP. And there are more examples. For instance, Hitchin talk about the example of the moduli space of Higgs bundles, and Stefan is mentioning Gucci-Hansen spaces, and there are a large class of examples of this. Sometimes you only know one side of the duality and the other side is not obviously clear. So what is this twistor space description? Well, in the case of hyperkähler geometry, Hitchin taught us that it's very convenient to encode the geometry of this M prime in terms of a slightly bigger space, Z prime, which is a twistor space of M prime. So you basically take the product of a sphere with this original manifold, and the sphere is parameterized by some variable zeta, and you have a complex symplectic structure that you can write in terms of the Kähler forms on the base in this linear combination. Now locally in some patch on this twistor space you can find some Darboux coordinates such that this symplectic form takes a canonical form like this. So you have some Darboux coordinates eta, lambda, mu, lambda, and you have this symplectic form. Now, if you have some overlapping patches, then these coordinates are related by symplectomorphisms encoded in some generating function that depends on this eta, mu, and the parameter zeta on the twistor fiber. And the key point here is that if you have a U1 isometry, certain U1 isometry, then these generating functions become independent of zeta. On the other side, I told you we have this quaternion Kähler picture. So that is slightly more involved, but it works in a similar way. So you have some metric on M, and it's convenient to also encode that in a bigger space, a twistor space Z, which is now just simply a product of M and CP1, but it's a non-trivial fibration of CP1s over M. And it turns out that this space does not have a complex symplectic structure, but it has a complex contact structure. That's a kind of an odd-dimensional version of symplectic geometry. And in a similar way, locally, you can find some complex Darboux coordinates such that there is a contact one form that takes a canonical form, like this. So you have some d alpha, and then you have a connection term here, which encoded in these xi and xi twiddle. So this basically this is like a foliation of symplectic spaces in terms of this parameter alpha. Now in this case, on overlapping patches, these Darboux coordinates are related by contact transformations, so transformations that preserve this contact one form. And this generically depends on all these coordinates xi, xi twiddle, and alpha, but it does not depend explicitly on the parameter t encoding the twistor fiber here. And here the key point is that if you have this U1 isometry, then this generating function is independent of this contact coordinate alpha. And effectively this means that this contact transformation reduces to a symplectomorphism acting on the subspace xi and xi twiddle. So let me give you just a recap of what I said. You have two twistor spaces, one of which is a complex contact manifold, the other is complex symplectic. You have a set of Darboux coordinates eta lambda, mu lambda, and zeta. On the other hand, this side you have these Darboux coordinates encoding the contact structure. An important point is that if you look at the opposite, if you think of Z prime as fibered over CP1, then the fiber is a complex manifold. It's a complex torus. But in this case, it's not a complex manifold, so the fibration is non-trivial, and this plays an important point in this wall crossing story. So what is the correspondence? Well, at the level of twistor spaces, you basically identify the Darboux coordinates like this. So you identify this xi with eta, xi twiddle with mu lambda, and the coordinates on the twistor fiber are related by a phase transformation. And they are described by the same transition functions. So this generating function, h xi xi twiddle, is identified with this one on the hyperkähler side. And this only works if you have these U1 isometries. But you may ask, so here I've identified these Darboux coordinates and the twistor fiber coordinate, but in fact on the stringy side, on the QK side, we have this additional coordinate alpha. What is the role of this alpha? So it's actually, it corresponds to a holomorphic section of a line bundle over this twistor space Z prime associated to the hyperkähler manifold. And this bundle has a crucial property that it's trivial along the CP1 fiber. And then by a standard construction in twistor theory, this descends precisely to a hyperholomorphic bundle L on M prime with a connection lambda, which is explicitly given in terms of this coordinate alpha. So this is how you get from manifold M to a hyperkähler manifold M prime equipped with a line bundle. So now we would like to use this relation to understand this wall crossing problem. Sorry, I forgot to say that this is because of this construction you have a manifest hyperholomorphic structure because this curvature is of type 1, 1 in all complex structures. So in order to use this, we have to review a little bit on how wall crossing works in field theory. So are there any questions before I proceed? Okay, so in the case of n equal to supersymmetric field theories in 4 dimensions, we look at theories with a certain gauge group G, which is broken to U1 to the R on the Coulomb branch. We restrict to no flavors for simplicity. So in this theory, there is some moduli space of vacua, B, which is some rigid special Kelly manifold. And there is some electromagnetic charge lattice, or a local system of lattices fibered over B. And the fiber over each point is the lattice Z to the 2R. And we have some electromagnetic charges, P lambda, Q lambda. So crucially in this theory, there is a central charge function, Z prime, which is given explicitly in terms of derivative of the prepotential and coordinates on this manifold. Now what happens is that when you take this 4-dimensional picture, you have this moduli space of vacua B, and you compactify it down to 3 dimensions. You get this bigger moduli space. So effectively, the theory in 3 dimensions is a sigma model with target space M prime, which must be hyperkähler because of supersymmetry. And topologically, this is a torus fibration over the original Coulomb branch, where the torus fiber is parameterized by the Wilson lines of the 4-dimensional vector fields. And what you get from this construction is also an explicit metric on this M prime. It's known as the semi-flat metric because it is flat on the torus fibers. And it's simply given by the metric on the Coulomb branch times the metric on the torus with the radius of the circle as a parameter. You get the 1-parameter family of metrics in this way. So this is precisely the rigid CMAP metric. Now, this is kind of the classical approximation, but at finite values of R, there will be instanton corrections to this metric that comes from Euclidean BPS states that wind around the circle. So in the 1 instanton approximation, they will take following form. You have the original semi-flat metric, and then you get some instanton term, which is weighted by e to the minus the radius to the central charge, and you have some type of theta angle term here involving the Wilson lines. And it's all weighted by the BPS index, which counts the number of BPS states in the theory. So what is this omega? Well, omega is some function, some integer valued function from the charge lattice. It's known as the second helicity supertrace. So here you have this insertion of minus 1 to the 2j that was discussed in Miranda's talk, and you also have to insert an additional factor of j3. So J3 is a generator of the little group in 4 dimensions. So this counts BPS states with sign, and it's locally continuous as you vary the parameters in B, but it can jump discontinuously on certain real codimension 1 manifolds in B, which are the walls of marginal stability. So those occur when the central charges of 2 BPS states align. And this corresponds to some decay from some BPS state of charge gamma into BPS states of charge gamma 1 plus gamma 2. And the wall crossing is simply to determine how does this omega behave compared to starting from one side of the wall and jumping to the other side of the wall. So you want to understand this difference where Z minus and Z plus are 2 points infinitesimally displaced on both sides of the wall. Now, how to do this in complete generality was solved by Kontsevich and Soibelman. So then we have to introduce some formalism. So they say, okay, you introduce a complex symplectomorphism that acts on some variable x gamma, it should be a prime here, and it acts in a certain way that it multiplies with this factor that depends on this BPS index. So this x gamma, at this stage, there are some holomorphic Fourier modes on a certain complex torus, like a complexification of this charge lattice. And what Gayotomo and Knightsky said is you should identify this complex torus that appears in the KS story with the fiber of this fibration of the twistor space over CP1. So if you do that, then it means that you get an explicit expression for this x gamma in terms of these Darboux coordinates on twistor space. And this is precisely like a type of twistor space version of this theta angle that appears in the instanton corrections to the semi-flat metric. So here is the formula. It tells you that if you take certain infinite product of these symplectic transformations ordered in a certain way on one side of the wall, you should get exactly the same result if you take a product ordered in the opposite way on the other side of the wall. And since these symplectomorphisms do not commute, that requires that the omegas jump in a certain way in order for this formula to be true, and that's precisely the wall crossing formula. So this allows to express omega on one side of the wall, say z plus, in terms of the spectrum on the other side. And importantly, it also ensures that the complex symplectic structure is smooth as you cross the wall. So the simplest example of this is the sort of famous pentagon identity that occurs. You have two charges with inner product 1 and the same BPS index, then you will get this pentagon identity that appears, for instance, in the SU3 Agios-Douglas quiver theory. But this gives you an infinite series of non-trivial identities between these symplectomorphisms. So what does this apply for the story of the moduli space metric? Well, I said that this semi-flat metric gets instanton corrections like this. Now, those instanton corrections are discontinuous across the wall, but you would expect that the moduli space metric should be smooth. And in fact, you have to describe the corrections from multi-instanton effects to this metric, and you do it by giving an instanton correction to these Darboux coordinates. And as GMN showed, the correct Darboux coordinates are obtained as solutions to a non-trivial integral equation that involves these BPS degeneracies. And the statement is that the resulting metric is smooth across a wall precisely when these omegas satisfy the Consiver-Solomon wall crossing formula. So that concludes the review of the Seiberg-Witten story. So let's now see what we can do with this in terms of the stringy compactification. So we change gears and we say, let's look at type 2 Calabi-Yau string compactifications. Well, the charge lattice will now become some D-brane lattice, say H3 or H even of the Calabi-Yau manifold. I already said that the moduli space which is relevant is some QK manifold, which correspond either to the hypermultiplet moduli space of type 2 on X, or via this CMAP procedure, the vector multiplet moduli space on X cross S1. So let's, for definiteness, just fix one of these. Let's take M to be the hypermultiplet moduli space of type 2A on X. So in that case, you can see that M is coordinate size explicitly by these coordinates which correspond to the complex structure moduli of X. Phi is the dilaton. Zeta and zeta twiddle are the Ramon-Ramon scalars that come from periods of the 3 form, and they parameterize the intermediate Jacobian of this Calabi-Yau. And you have this additional guy here, which is the NS axion. So it's the dual of the B field in 4 dimensions. And the topology of this space is kind of similar to the space, this hyperkähler modular space we had before. You have the complex structure moduli space here, the base, you have a torus fibration of intermediate Jacobians, parameterized by these Ramond scalars. But in addition, in this stringy picture, we have some circle fibrations over this torus, parameterized by this sigma. So this is the topology at the fixed weak coupling, at the fixed value of the coupling. So this is some twisted circle bundle over the torus. Now the point is that the translations of these scalars are broken by D2 brane instantons, and translations of this NS axion is broken by NS5 brane instantons. And the analog of the semi-flat metric is the one loop corrected CMAP metric. So it takes a form very similar to the one that we had in the field theory story. So you start with some CMAP metric here that is explicitly known. Then you will have instanton corrections coming from D2 branes wrapping 3 cycles. So it's weighted by some index, and it goes like e to the minus central charge divided by the string coupling and this theta angle. But then you also have these NS5 brane effects, which are weighted by e to the minus 1 over the string coupling squared, and some theta angle, and multiplied by some coefficient that we really don't know what it is in general. And you see that these are exponentially suppressed in the weak coupling limit. An important point that in the absence of these effects, then you will have one continuous isometry preserved, because shifts of sigma will be preserved when the NS5 brane effects are not present. So you will have some isometry, d sigma of m, and that will lift to a holomorphic isometry of the twistor space, which is precisely of the form needed to invoke this QK-HK correspondence. So what happens is that if you start with some general complex contact transformation on this twistor space Z, under this correspondence it must decompose into a symplectomorphism of the dual twistor space and a gauge transformation acting on this section coming from this coordinate alpha. And this contact transformation must preserve the connection on L, which is inherited from the contact structure. So if you work this out, you find that the action on such a transformation must reduce to a symplectomorphism like this here, and a certain action on this section, which corresponds to a shift of the alpha coordinate, which depends on this BPS index and its certain function of the coordinates x gamma, which is given by the Rogers dilogarithm. So it's a combination of the standard dilogarithm with some additional terms here. And in order for this to be consistent with wall crossing, we must ensure that this is smooth across the wall of marginal stability. So this contact transformation must preserve a kind of a generalization of the Concevier-Soberman wall crossing formula that involves these V gammas instead. In order to write what this implies, it's very useful to just put everything over onto one side. So I've just written it like this. So epsilon s is some sign that encodes depending on which side it comes from. So this will give you some complicated product of transformations that should give unity. And for the total transformation on this section to be trivial, it requires a very non-trivial identity between Rogers dilogarithms weighted with this BPS index. So this is a consistency condition for the construction of this line bundle. And this construction was independently found recently by Andy Knightsky. So as I said, this requires some very non-trivial identities for the Rogers dilogarithm, the first of which is the famous pentagon identity. It just involves these 5 terms. But in general, you will have a very complicated identity to prove. And in fact, yes?
So these chi coordinates,
yes,
these are these 4 contra coordinates, right?
Well, yes, you,
They satisfy this integral equation, which is like a TBA equation.
that's right.
So there's some old stuff known that TBA relations, if you rewrite them in terms of y functions,
Yes.
satisfy similar relations.
That's
So
right.
this goes back to
Yes, that's
use
right.
that essentially?
Yes, that's right. So, in fact, there are many of these formulas which are known. In particular, there are many of them known. They are associated to cluster algebras for simply laced quivers, for instance. But the point is that these numbers here are completely general. So if you look, so this is like a generalization of those, and it will reduce to many of these. So I have a comment about that later, but you're right.
So does it tell you, can I ask another question?
Yes.
So when you look at those TBA equations, it wasn't clear to what kind of integral system that would correspond to.
Uh-huh.
So can you say something about that?
Well,
Given these identities?
so I have some speculations in the end as to. I mean, this has the smell of a kind of a geometric quantization of a complex integrable system that we really don't understand. So I don't really want to make some remarks, but yes. So this is a kind of generalization of those types of identities that are known for cluster algebras of simply laced quivers and also some non-simply laced ones. But it turns out that this general formula, in fact, follows from the Motivic Consiver-Solomon wall crossing formula. So that's a conjectural formula, but you can show that, in fact, from that formula, this follows. So how much time do I have?
20 minutes.
Okay, so then I can sketch how this works. So in fact, there is a generalization of the Consiver-Solomon wall crossing formula, which is called the Motivic one, and physically it pertains to the so-called refined BPS index, or protected spin character, that has an additional parameter q, like a q deformation of omega, that encodes the spin degrees of freedom of the BPS state. And in that case, these symplectomorphisms should be upgraded to a certain product of quantum dilogarithms. So you have this product of quantum dilogarithms that depend on these omegas, and the x's now become promoted to x hats, which parameterize so-called quantum torus. And if you play the same game that we did before, we shuffle all of the stuff onto one side, then you will write this as some identity between these Motivic transformations. And we want to understand the semi-classical limit of this formula. So when this parameter q goes to -1 conventions. So what you can do is you can follow philosophy of many people. So originally Fadeev, Kasheyev, Fokin Goncharov, and also recently by Kasheyev and Nakanishi, that you rewrite this product of quantum dilogarithms as an operator acting in some Hilbert space. And then you write the vev of this operator as a kind of a path integral. And the semi-classical limit corresponds to taking the saddle point of this path integral. And at the saddle point, the integrand is precisely an exponential of dilogarithms. In fact, Rogers dilogarithms. And if you do this specifically for the Ks formula, the total operator that you have must be trivial, because you have this trivial product. And in fact, if you do it carefully, you find precisely the dilogarithm identity that is required to construct this Lie bundle. So this indeed generalizes various previous formulas that were conjectured and proven in some cases by Nakanishi, Bernard Keller, and others associated to cluster algebras. But in order to complete the story, we have to also show that, in fact, the metric that you get is smooth across a wall of marginal stability. And that requires that these x gammas satisfy again this thermodynamic beta ansatz of this integral equation. But you have an additional constraint, which is that this alpha coordinate, or this section of the bundle, you have also an explicit integral form for this section that involves this ns axion, and then it involves an integral over Rogers dilogarithm in contrast to the K-S integral equation, to the integral equation of Gayotto-Moore-Knight scale, where you have logarithms of the x's here. So in fact, this expression determines this hyperholomorphic connection because it was given explicitly in terms of derivatives of this alpha. So you will get a kind of a semi-flat form of this connection plus instanton corrections coming from these d-branes. So to summarize, there is this general duality between hyperkähler and quaternion Kähler manifolds which have isometric circle actions. So we have used sort of one specific example of this duality. And using that, you can see that the twistorial construction of the d-instanton corrected hypermultiplet moduli space that comes from n equal to string compactifications can actually be encoded in this hyperholomorphic bundle on a dual hyperkähler manifold. And the consistency requires some non-trivial identities for the Rogers dilogarithm, which are in fact a consequence of the motivic wall-crossing formula of Kontsevich and Soberman. And there are some very surprising and interesting relations with cluster algebras that appear in this construction. Now, maybe the main missing point here is the NS5 branes. So we actually, if you include NS5 branes, then this duality breaks down because the continuous isometry that we use is broken. So we need some other construction. But there is some hint that follows from our work that I would like to just mention, which is that very similar construction have been found recently by Fock and Goncharov when they look at geometric quantization of cluster varieties. This is some mathematical construction associated to cluster algebras. And if we reinterpret this, so the point is that in their construction, this Rogers dilogarithm plays a role very similar to what we observe. And this suggests that this torus that we have, the fiber of the twistor fibration, should be identified with the so-called cluster seed torus, such that M prime is in fact a cluster variety equipped with a hyperkähler metric. And the key point is that this line bundle that we have then gets interpreted as kind of a pre-quantum line bundle in terms of geometric quantization. But what these gentlemen do, they in fact construct something much more general. They construct a higher rank vector bundle that depends on one parameter, h bar, which is kind of a quantization parameter, which is rational. And sections of this bundle have precisely the form that we expect from NS5 brane instanton corrections. So our sort of tentative conjecture is in fact that this, in the case when this h bar is an integer, this should in fact be identified with the NS5 brane charge, and you can encode NS5 brane effects in terms of sections of this bundle. But it's sort of suggestive. We don't know really how to flesh out this proposal. Thank you.
Okay, we have some
I'm
extra time.
wow, I thought it would be longer.
Time for questions.
So you have a Calabi-Yau, I mean, in Taipei language with h21 equals
Yes.
0, rigid Calabi-Yau. So that you have just this single hypermultiplet. Anything special happening there?
Well, the point is that if you compactify in a rigid Calabi-Yau, you don't have wall crossing. So there might still be an interesting issue of instanton corrections. But so in fact, in the case of compactification on rigid Calabi-Yau, you have this universal hypermultiplet metric. Now in that case, classically, it's just a coset space. So I mean, we have tried to understand quantum corrections of this using some automorphic techniques based on the subgroup of SU2,1, but you wouldn't expect this to exhibit any wall crossing properties. So, but yeah, that's certainly one one setting where you can try to understand more about the NS5 brains.
Have you tried using duality with the heterotic?
So that's maybe the so that in some sense should be a simpler. The heterotic side, it's exact, so that should be a simpler thing. But to actually do the mapping has been sort of attempted many times, and then I think it's not really been worked out. I mean, recently there was some interesting paper of Jean-Louis and Paul Smith, right? And so I think there's a lot of interesting work to be done there, but it hasn't really been used so much.
I'd like to still ask a question. When you say smoothness of the metric when you cross a wall, what do we actually mean? Because the metric wasn't smooth and isn't smooth before and after crossing the wall.
Well, I mean that if you look at the instanton, if you just take the one instanton approximation, you have explicitly this omega appearing, so that's definitely not smooth. So I'm not talking about, let's say, the one loop singularity. That will not be smoothed out. But the effects of the instantons, which are discontinuous to cross the wall, they will be smooth. So you will not have a discontinuity in omega as you cross a wall.
Are there maybe any walls in the directions of the dilaton axion system?
Yeah, so I mean, then you're actually talking about wall crossing, NS5 brain, how those will affect wall crossing, right? And that, I don't know. What does it mean to have wall crossing in the presence of NS5 brain effects? But you're right that the one loop singularity is not smoothed out by the instanton corrections, but that's a different issue.
If no more questions or comments, then we thank Daniel again.